Welcome back to another Fluent flow simulation video. Today is going to be the final project that we're dealing with in this class. Today we're going to be doing flow around a cylinder. So what we're going to do is we're going to build the geometry and the meshing that I'm going to use to do the Reynolds number for 0.01. And then we're going to look for all of these things. So I've already set up all of the cases, but what we're going to do today is move just to case 2. And we're going to take a look at what I did and why I did those things. So here we are in the design modeler, and you can see that the surface is already set up. So on the sketch, I have only a few dimensions that I needed to work with. We're doing a 1 meter hole, 25 meters high, halfway up, and then a 10-meter offset from the front because there's not a lot happening in the front, it's all behind it. So create this surface from the sketch, and now we can move on to our mesh. In our mesh, I have two different things going on. I have face meshing and edge sizing. The initial mesh element size I let be 10 centimeters, and I let the edge sizing on all 4 edges be the same element size. And then face meshing, I went ahead and just did triangles best split, and after much deliberation my computer came up with this mesh. You can see here that I have some pretty good definition around the circle, which is what I want, and it is pretty even all the way around with no obvious tight spots or gaps. So once you go through and name your sections, then you can exit the mesher and we'll move on to the setup. Now it's on to the setup. In the setup, in this case, we have a viscous laminar flow. I'm going to open up a file for my Reynolds numbers so I can make sure that I get the correct Reynolds number for this case. And it has all of the Reynolds numbers that I created. For 0.01, we're going to have a viscosity of 10,000. So there's our viscosity of 10,000. Change, create, close. It's going to take a few tweaks to be able to get this to converge properly. Make sure that your inlet, outlet, symmetries, and cylinder walls are all labeled appropriately and are acting properly. We're going to come over to methods. In this case, first thing I'm going to try is a simple pressure velocity coupling. And then we're going to try to solve this. Let's run the calculations. It shouldn't take more than, a few iterations. Let's check the boundary conditions. In this system, I have 2 separate cases that will be happening. On the cylinder, I will be having a stationary wall, and I will also have a rotating wall. We're going to start with the stationary wall. We'll initialize and calculate. And there we have it. Calculation is complete. Let's take a look at some contours and graphs and try to interpret this stuff to make sense of what is happening. First thing I want to look at is a contour. Actually, let's open up the path lines first. So here we are going to see So here with these path lines, I'll move this to the bottom. With these path lines, what we're going to see is the velocity changes as the airstreams move around the stationary cylinder. And you can see, because it is such a high viscosity, it's basically ignoring all the inertial forces and gluing itself around the cylinder. We're also going to grab a few contours. We have a velocity contour here, and that makes sense that we should have low velocities in front of and behind the cylinder, and high velocities where it's getting pinched on the tops and bottom. Let's grab another contour. This is going to be our pressure contour. Not much going on here. We have a very high pressure area at the stagnation point at the front, and on the trailing edge it is a low pressure area. Last couple things we want to look at. I want to look at some forces. I need to grab the forces on this that are acting in the positive x direction. So here, you can see we have all of our forces. That force along this direction vector, in the positive x direction, we have a total force of 920,000 newtons. The coefficients are also going to be via pressure and viscous drag. It's going to give us a total drag coefficient of 1.5 million. So, now that we're done with this, the last thing that I have to do is I have to put a spin going anti-clockwise on the ball and look at the lift that is generated from that spin. Yeah. So now we're done with. Let's take a minute to change our setup a little bit. We're going to come in and change this wall for the cylinder to be a rotating wall. We're going to rotate about the point 0, 0, which the way that I built this geometry is the center of my cylinder, and we're going to rotate at a speed anti-clockwise at 5 radians per second. With all things being equal, we're going to initialize again and run a calculation. It took 129 iterations to converge. To make sure that we get what we think we should have, we're going to look at the streamlines. So here's our streamlines. And what I should see, I'll drag this down here. What I should see with these streamlines is the velocity should be a good bit higher down here below, which will cause a lower pressure. With a lower pressure, I should have some negative lift or some downforce. So there we go. That's everything for this. I hope that you guys enjoyed the video. Don't forget to like, comment, subscribe, and I will see you guys in the next one.